Welcome to Lecture 3 Advanced Calculus Real Analysis, Section 1.3 of the text Advanced Calculus by Patrick M. Fitzpatrick, second edition. This is Dr. Gilbert Eyabi. Our topic today would be Inequalities and Identities. Subsection 1.3.1 Definition: the absolute value of x. The absolute value of x equals x if x is greater than or equal to 0, and it equals negative x if x is less than 0. For example, the absolute value of 5 is 5 because 5 is greater than 0. The absolute value of negative 5 is negative 5 right here, and negative 5 is 5. So the absolute value of x is always non-negative, i.e., it is always greater than or equal to 0. It follows from this definition and the positivity axioms that for any two real numbers x and k, where k is greater than or equal to 0, absolute value of x is less than or equal to k if and only if negative k is less than or equal to x, which is less than or equal to k. I need you to remember this inequality because we would use it often. Moreover, I need you to also observe that for any real number x, negative absolute value of x is less than or equal to x, which is less than or equal to the absolute value of x. Once more, I need you to remember this inequality because we would come back to it. Now, let's look at example 4. The absolute value of x plus 3 is less than or equal to 7 if and only if, go back to this inequality right here, which I ask you to remember. Negative 7 is less than or equal to x plus 3, which is less than or equal to 7. And if I subtract 3 on all sides, I end up with negative 10 is less than or equal to x, which is less than or equal to 4. And observe that 4 is less than or equal to 10. So I can extend this inequality to negative 10 less than or equal to x, which is less than or equal to 10. In other words, going back to this inequality here, I can say that absolute value of x is less than or equal to 10. This is a form of argument that we will use often in this course. So, if I were to summarize, I would say that if c and d are real numbers, such that c is less than or equal to x, which is less than or equal to d, without loss of generality, the absolute value of c is greater than or equal to the absolute value of d, just like in our case, the absolute value of negative 10 is greater than or equal to the absolute value of 4, then we can say that the absolute value of x is less than or equal to the absolute value of c. That's what we have here. Or if the absolute value of d were greater than or equal to the absolute value of c, then we could say that the absolute value of x is less than or equal to the absolute value of d. Again, we would employ this technique in some of our arguments. Now we proceed to the first key result of this section, Theorem 1.3.2, the triangle inequality. For any pair of numbers a and b, that means a and b are real numbers, the absolute value of a plus b is less than or equal to the absolute value of a plus the absolute value of b. This does not necessarily hold with subtraction. So the triangle inequality only deals with addition. Now, the generalized triangle inequality says the absolute value of the sum of ai, I from 1 to n, is less than or equal to the sum of the absolute values. Okay? So the absolute value of the sum is less than or equal to the sum of the absolute values. Proof. You would think that such a profound result would have a very complicated proof, but no, it's a very easy, straightforward proof. So we want to prove that the absolute value of A plus B is less than or equal to the absolute value of A plus the absolute value of B. I.e., we want to prove that negative, all of this, is less than or equal to A plus B, less than or equal to all of this. Remember what it means for the absolute value of x to be less than or equal to k. It means that negative k is less than or equal to x, which is less than or equal to k. So we are applying that here. So this is what we want to prove. Now let's go ahead and prove it. Remember one of those inequalities I asked you not to forget? Well, here we are. Negative absolute value of A is less than or equal to A, which is less than or equal to the absolute value of A. Call that inequality chain 1. Also, negative absolute value of B is less than or equal to B, which is less than or equal to the absolute value of B. Call that inequality chain 2. Add 1 and 2 and we get negative absolute value of A minus absolute value of B less than or equal to A plus B, which is less than or equal to absolute value of A plus absolute value of B. Hey, wait a minute. What did we just get? Go back here. Exactly what we are trying to prove. Hence, we've succeeded to show that the absolute value of A plus B is less than or equal to the absolute value of A plus the absolute value of B. End of proof, and we're done. Beautiful, easy, straightforward. Okay? Now let's visit this proposition. Proposition 1.3.3. For a number A and a positive real number R, the following three assertions about a number X are equivalent. These three assertions are equivalent. The absolute value of X minus A is less than R, A minus R less than X less than A plus R, and X is a member of the open interval A minus R, A plus R. Proof. The proof is actually trivial, but I'm still going to go ahead and give it. We're going to prove that 1 implies 2, 2 implies 3, and 3 implies 1. That is how you prove things involving equivalence of several statements. Proof. 1 implies 2. Suppose the absolute value of X minus A is less than R. RTP, that means required to prove. We want to prove that A minus R is less than X, which is less than A plus R. We have to start with what we have to get to where we're going. So, but absolute value of X minus A less than R, what does that mean? It implies negative R is less than X minus A, which is less than R. I add A to all sides and I end up with A minus R less than X less than A plus R, which is what I'm trying to prove. So I'm done. 1 implies 2. Now let's prove 2 implies 3. Suppose A minus R is less than X, which is less than A plus R. Required to prove X is an element of the open set A minus R, A plus R. But A minus R less than X less than A plus R implies that X is an element of the open interval A minus R, A plus R by the very definition of the open interval A minus R, A plus R. So really there is nothing there to prove. And we're done with 2 implies 3. Now let's look at 3 implies 1. Again, 3 is X is in this interval, and we want to prove that the absolute value of X minus A is less than R. Suppose X is a member of the open interval A minus R, A plus R. we want to prove that the absolute value of x minus a is less than r. But x, a member of this interval, implies that a minus r is less than x, which is less than a plus r. And I go ahead and subtract a from all sides, and I get negative r less than x minus a less than r, which implies that the absolute value of x minus a is less than r, and that is statement 1. And that proves 3 implies 1, and hence the proposition. And we're done. Now, at the heart of many arguments in analysis lies the problem of estimating the sizes of various quotients, differences, and sums, and of simplifying various algebraic expressions. As a companion tool to the triangle inequality, we would now establish 3 algebraic identities. But before we get there, I want you to recall that a raised to the power n equals a times a times a times a times a n times. Okay? Now, let's go ahead and dig in and see those 3 algebraic identities. Number 1 is known as the difference of powers rule, subsection 1.3.4. It states that a to the n minus b to the n equals a minus b times summation k from 0 to n minus 1, a to the n minus 1 minus k, b to the k, where n is a natural number, a and b are real numbers. Now, to break that down, we're saying that a to the n minus b to the n equals a minus b times a to the n minus 1 plus a to the n minus 2 times b plus a to the n minus 3 times b squared plus a times b to the n minus 2 plus b to the n minus 1. Now, I want you to observe that the sum of the exponents in each of these terms is n minus 1, a raised to the n minus 1. And over here, we have a to the n minus 2, b to the 1, n minus 2 plus 1 is n minus 1. And over here, we have n minus 3 plus 2, and that sum is n minus 1. So the sum of the exponents of each of these terms right here is n minus 1. We would use this idea at some point in this course. Now let's go ahead and look at a common example. X to the 7 minus 1 by the difference of powers formula would be x minus 1 times x to the 6 plus x to the 5 plus x to the 4 plus x to the 3 plus x squared plus x plus 1. When do we use this? Well, we haven't treated limits yet in this class, but I suspect that you've seen the idea of limits back in Calculus 1 or Calculus 2. So, compute the limit as x approaches 1 of x to the 7 minus 1 divided by x minus 1. You see that if I substitute 1 for x, I end up with 0 over 0. Now, if you are not allowed to use L'Hopital's rule, and I just want you to use algebraic properties to find the limit, then you would have to use the difference of powers formula. In that case, x to the 7 minus 1 will be factorized out as x minus 1 into all of these divided by x minus 1. And if I cancel out x minus 1, this reduces to limit as x approaches 1 of x to the 6 plus x to the 5 plus x to the 4 right down to 1. And if I substitute in 1 for x, that gives me 1 plus 1 plus 1 plus 1, 7 of them, and my answer is 7. We will see this some more when we treat limits in this class. Proof. A more rigorous proof would apply the principle of mathematical induction, but what I want us to do here is just to verify that this is the case. So I'm going to start with the right-hand side and then show you how we get the left-hand side. So starting with the right-hand side, I have a minus b into a to the n plus 1 plus a to the n plus 2b and so on and so forth, right down to b to the n minus 1. And if I multiply this out, I would get a to the n plus a to the n minus 1b plus a to the n minus 2b squared plus minus a to the n minus 1b minus a to the n minus 2b squared minus b to the n. And then observe that a to the n minus 1b cancels out with a to the n minus 1b. Same thing with a raised to the power n minus 2 times b squared cancels out with this, and so on and so forth, and I'm left with a to the n minus b to the n. So that is a very easy way to verify the difference of powers formula, but we can actually provide a more rigorous proof using the principle of mathematical induction. So I'll leave that for you to write out x to the 8 minus y to the 8. Of course, it will be x minus y times, go ahead and finish that up. The second identity we would be interested in would be subsection 1.3.5, the geometric sum formula. It says summation k from 0 to n of r to the k equals 1 minus r to the n plus 1 divided by 1 minus r, where r is different from 1. And that happens for every natural number n and for every real number r, just that r has to be different from 1. In other words, if we were to break this up, we're saying that r to the 0 plus r to the 1, recall that r to the 0 is just 1. So r to the 0 plus r to the 1 plus r squared plus r cubed plus r to the n equals 1 minus r to the n plus 1 divided by 1 minus r, provided that r is different from 1. Again, observe that if r is 1, then the denominator vanishes, and mathematicians don't like that. Proof. The proof of the geometric formula follows the principle of mathematical induction. As a matter of fact, whenever you are asked to prove something for every natural number n, it always goes by the principle of mathematical induction, whether you're told or not. Okay? Always use the principle of mathematical induction. I'm going to do just step 1, and I'll let you do the next 2 steps. Remember, proof by mathematical induction, you have the basis step, you have the induction hypothesis, and you have the inductive step. So let's look at the basis case, or some people call it the base case, when n is 1. When n is 1, the left-hand side will be summation k from 0 to 1, r to the k, which is r to the 0 plus r to the 1, which is 1 plus r. Good. The right-hand side would have 1 minus r to the 1 plus 1 divided by 1 minus r, which equals 1 minus r squared divided by 1 minus r. Following the difference of powers formula, we break this down as 1 minus r times 1 plus r divided by 1 minus r, and we cancel out the 1 minus r, and we're left with 1 plus r. So the left-hand side equals the right-hand side, and that means the basis case is done. We now have to go through the induction hypothesis and the inductive step. Example, compute for me this sum, 1 plus 1 half plus 1/4 plus 1 over 10,000. You can fold the sleeves of your shirt and write it all out from 1 to 10,000 and find the sum, or you could use the geometric sum formula to get the answer very quickly. All you have to do is observe that I can rewrite this sum as 1/2 raised to the power 0 plus 1/2 raised to the power 1 plus 1/2 raised to the power 2 plus 1/2 raised to the power 100. So my r is 1/2. And therefore, by the geometric sum formula, that equals 1 minus 1/2 raised to the 101 divided by 1 minus 1/2. And that is 1 minus 1 divided by 2 raised to the 101 divided by 1/2. And that flips over. That is 2 minus 1 over 2 raised to the 100. Usually, we will not be interested in the exact value. We will be interested at an upper bound. So we would say that this value, no matter how small 1 divided by 2 to the 100 is, this value is going to be less than 2, and that is what we are interested in. That is the geometric sum formula, GSF. And now the last of the identities is known as the binomial formula, subsection 1.3.6. It says a plus b raised to the n equals summation k from 0 to n combination k, a to the n minus k, b to the k for every natural number n and for all real numbers a and b, where we define n combination k as n factorial divided by k factorial times n minus k factorial. Now recall that with factorials, 0 factorial equals 1 factorial, and that equals 1. And n factorial equals n times n minus 1 times n minus 2 times 3 times 2 times 1. For example, 5 factorial is 5 times 4 times 3 times 2 times 1. Example: a plus b raised to the power 5 equals summation k from 0 to 5, 5 combination k, a to the 5 minus k, b to the k, and I can write that all out as 5 combination 0, a to the 5. I prefer using c because of the word combination. So we can write this all out as 5 combination 0, a to the 5, plus 5 combination 1, a to the 4, b to the 1, plus 5 combination 5, b to the 5. And all I have to do is to compute 5 combination 0, 5 combination 1, 5 combination 2, 5 combination 3, 5 combination 4, and 5 combination 5. So for example, 5 combination 2 would be 5 factorial divided by 5 minus 2 factorial times 2 factorial, which is 5 factorial divided by 3 factorial times 2 factorial. And I can write 5 factorial as 5 times 4 times 3 factorial. I do not have to go down to 1 because I want to cancel 3 factorial and 3 factorial. 2 factorial is just 2 times 1, and that gives me 2. And my answer is 10. And doing the same for all of these, you would get 1, 5, 10, 10, 5, 1. And of course, you may be asking, what about Pascal's triangle? Yes, you can also use Pascal's triangle. And if you do not know what that is, just look at any algebra text, or you can just Google Pascal's triangle, or you can contact me and I would gladly give you some insights into Pascal's triangle. Thank you very much. And lecture 4 would be on section 2.1, convergence of sequences. I'll see you later. God bless you.